What's up, pre-calculus students? Not sure if anybody is going to watch this, but I'm going to do it anyways. Unless I feel bad. It's the Unit 8 review. Did a lot of stuff in Unit 8. Let's just get to it. Starting with polynomials and end behavior and zeros and what things look like. And, when I did this in my class, I actually like to start with question number 3. Because if we could kind of sketch things, then we can go backwards and find the equations of things. What's easy information to know when we're graphing? From this equation, easy information, since it's in a factored form, since it's a product, zeros. 0, -2, 2. That's easy. Over here, what are the zeros? A lot of people think 0 because they see this number outside, but no. The number does not mean that you have 0. It's the x that you plug 0 into and get 0. Here, the number, you don't get anything from that. Just makes things go faster up and down and stuff like that. Anyways, the numbers that would make this 0 are -3, 2, and 5. Okay, now that means you have these points at 0, 0, at -2, 0, at 2, 0. Okay, -3, 0, 2, 0, 5, 0. But what other information can we get just by looking at this? It's easy to see, like, oh, this whole squared thing. This is like the multiplicity. I like to say the multiplicity is 1. Some people don't like to say that, but multiplicity is 1 of x because it's x to the first power. Versus 2 and -2, the multiplicities are 2. Now, why is that important? If you think about something like y equals x squared, what happens? Well, it's like, since its value's being squared, the signs don't change around that. Any even multiplicity, the signs don't change. It just bounces off of it. So that's just something to remember, that if your multiplicity is 2, your signs aren't going to change around that because you're just going to bounce. If you have a multiplicity of 3, which none of these have, but if you do have a multiplicity of 3, you're going to bend through. Why is that? Well, let's think about x cubed. As we take like fractions that are getting smaller and smaller and smaller to 0, get it cubed, they like really get close to 0 quicker than if it was just like a number to the first power. So this is why x cubed bends through. So multiplicities that are odd, except for 1, will bend through. Multiplicity of 1 just goes through, just like y equals x. How does y equals x looks like? It changes sign, it goes straight through. Okay, so just keep that in mind. It comes from those graphs. What else can I do? Well, like, we're going to use sine analysis a lot, so might as well like be comfortable with the sine analysis. This will help you for end behavior. Now, this is analyzing the signs of f. Okay. Now, what do? We plug in a value that is like outside our intervals, knowing that we have all of the possible sign change locations. We don't have to worry about any other points, or we don't have to test a lot of points, just 1 point, or else the signs are going to change. Plug in 3, you got a negative. This is 3 plus 2 squared, that's a positive. 3 minus 2 squared, that's a positive. Negative, positive, positive, we got a negative. Now, we could do the same thing with the sign analysis. I could plug in 1, check the signs, positive, negative, blah, blah, blah. Or, since you know the multiplicities, at 2, your multiplicity is 2, you're going to bounce. So that means your signs aren't going to change. You're going to go from negative values and then bounce off those. At 0, all the multiplicity is 1. Oh, you're going to pass through. And change signs. And then at -2, multiplicity is 2, you're going to bounce. So you're going to bounce off like this. And this is what your graph would look like. And it's like, well, how the heck do I know that it's going to look like that? Well, if you do the sign change and you understand multiplicities, no big deal. Another way you could figure this out is if you thought about like distributing everything. So this would be like x squared plus blah, blah, blah. And this is like x squared plus blah, blah, blah. Well, if you have an x squared and a negative x, that's a total of 5 x's, but it'd be a 5 negative x's. So this is x to the 5th. Odd powers are like x cubed, x to the 5th, have end behavior that are up and down like that. This is like y equals x cubed. Y equals negative x cubed looks like this. This is negative x to the fifth. That's why we have this end behavior here. So this is all good. Let's do the same thing here. Let's do a sine analysis. -3 to 5. Bounce off of 5. If I plugged in something like 6, this is the only one I'm going to check. Positive, 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 positive. Bounce off of 5 because the multiplicity is 2. So it's positive. Pass through 2. Pass through -3. Change signs, change signs. So positive, bounce, pass through, pass through. You could do one extra thing, which is find this y-intercept. That's when x is 0. That'd be a very large number. I'm not going to worry about that. So it's not going to look exactly like this to scale for sure. What else? Well, if I distribute this whole thing out, it would be 3 times x times x times x squared. That's 2, 3, 4 x's, 3x to the fourth. An even power will be up and up like x squared or down and down like -x squared. Same with x to the fourth and so on. So if you do those, it's easier to get like your equations like that. Start with your roots. X equals -3. Multiplicity is 3. Why? Because it bends through like x cubed. What does that tell me? Well, if I'm graphing or if I'm generating an equation, I know I'm going to have not x minus 3 cubed. That's what a big mistake people make. It's like -3. Okay, -3. No. You need to plug in -3 for x, and this needs to be 0. For that to happen, you need x plus 3, so that when you plug in -3, you get 0. You got x equals 0. The multiplicity looks to be 1 because you're passing through. So I need an x here. You got to bounce at 2. So x equals 2. The multiplicity is 2. That means you need an x minus 2, so that if you plug in 2, you get 0. But that multiplicity is 2. What else do you need? Well, there's some sort of a value, some leading coefficient that we need to take into account. Now, if I had an exact point somewhere besides 0, 0, like any of these points, I could use that point. Let's say this was like a point -1, 10. Well, that is an x comma y solution that I could plug in to find this unknown value a, okay? And that would give me the specific value if it's positive or a negative. But I'm not given any of those points, so I don't really know exactly what a is. But I know since this is going to be a 6th degree, like x times x cubed times x squared is x to the 5th, x to the 6th. I know that the end behavior of x to the 6th is up and up, just like x squared is. But this isn't like that. That's down and down. That's why I know I need a negative here. Now, I wish they gave you a different point. I wish they gave you something where it's like, I know this is a value. That way we can find the specific a value, but we'll do that on a future problem. Like this one. This one, I have a specific point here, 0, -3. We're going to use that to find a. Okay, what do I notice? Let's find the zeros. X equals -4, multiplicity is 1. X equals -1, multiplicity is 1. X equals 3, the multiplicity is 1. So it's going to be an x cubed. We're going to write it in factored form, thankfully. So this is j of x. J of x equals, okay, let's go x minus 4. No, not x minus 4, x plus 4, because I have -4. We're going to figure out this a in a second. Leave this leading coefficient as something we'll find. Then x plus 1 to make sure that we get this -1 plugged in, giving us a 0. And x minus 3 to get that. Okay, now, last thing, find out what a is. Well, it has this point 0, -3. That is an x comma y solution. Well, if I plug in -3 for y and 0 for x, I better have a solution. So I'd be able to solve and find a. That would make sure that this works. So this ends up being -3 equals a times -12. and we get a is positive 1/4. So the equation is positive 1/4. This looks good because the correct end behavior of a positive x cubed graph, x plus 4, x plus 1, x minus 3. End behavior, as I go to the right for my x's, my y's go up. As I go to the left on my x's, my y's are going down. Right and up, left and down. So as x goes to infinity, j of x is going to positive infinity. As x goes to negative infinity, j of x goes to. Okay. I'm not gonna, this problem stinks because I don't want to use the quadratic formula. I'm going to just describe the end behavior. Positive leading coefficient, x cubed, up and to the right, down and to the left. Okay, so same thing as this. As x goes to infinity, f of x is going to go to positive infinity. As x goes to negative infinity, f of x is going to go to negative infinity. I don't think we're going to ask you to use the quadratic formula for your test, so I'm not going to. What you'll find is that you can factor out 3x and you get x squared minus 4x plus 1. You can't factor this. We have a 0 at 0. We probably have 2 more zeros from this. But use the quadratic formula to find it. You can see on the key what it is. There's 3 roots. Don't worry about what they are. Y-intercept, that is easy to find. I plugged in. Y-intercept is when x is 0. This is very important. Plug in 0 for x to find the y-intercept. There's a couple really good questions. Oh, my thing just went. See if that brings it back. Yeah, there you go. Good questions on your quiz where they gave you a y-intercept. You have to find certain information. You plugged in 0 for x, you get 0. So the y-intercept is at 0, 0. My thing just froze. All right. Write a polynomial function that can be modeled by the given graph, leaving factored form. Make sure the y-intercept is 5. This is like the same deal as what we kind of just did earlier. We got x equals negative 6, multiplicity is 1. We got x equals negative 2, the multiplicity is 1. We got x equals 1. Oh, thankfully, we get to leave it in factored form. The multiplicity is 2. We're bouncing off of that. We got x equals 5. The multiplicity is 1. Y equals some coefficient, some constant, times x plus 6 gives me the negative 6. X plus 2 gives me that negative 2, 0. X minus 1 gives me that 1 as a 0. Square it. And x minus 5 gives me that 5. We have a y-intercept at 0, 5. So when x is 0, y must be 5. 5 equals a times 6 times 2 times negative 1 squared. 1 times 5. So 5 equals, I'm going to just divide by 5. You could have done all this out, but whatever. 1 equals 12. A equals 1/12. Divide by 12. So y equals 1. That's a 12. 1/12. X plus 6. X plus 2. X minus 1 squared. X minus 5. Oh, yeah. All right. Now, we did the sign analysis here for sketching. Where does that help us? When we want to find inequalities. If I asked you, when was this less than 0 or greater than 0? Well, obviously, no, less than 0, that's like a y coordinate of 0. Less than 0 when you're under the x-axis. That's when you have negative values. Negative values are less than 0. Positive values are greater than 0. That's important to know. That's very important to know. I'm just going to write this, okay? Because these sign analyses will help us solve these inequalities. Now, less than 0, negative, greater than 0, positive. What gets in between positive and negative changes? It's if we have zeros. We want to have a 0. The zeros are where we can change signs. Also, asymptotes are where we can change signs. Vertical asymptotes, jumps as well, but we don't have to worry about jumps. So what we want to do with these equations is actually find the zeros, because those are the possible sign changes. Now, to find the zeros, we should factor set equal to 0, and you get 3 and negative 2. Obviously, we're looking for two numbers to add to get this and multiply to get this. We've done it so many times that we should know. And we're not doing a cross thing. I'm just knowing, like, if I distribute this, it's x squared plus negative 3x plus 2x minus 6. That's negative 3 plus 2x minus 6. The two numbers add to get negative 1. The two numbers multiply. This is plus negative 3 times negative 2, right? The two numbers multiply to get that. So I want to make sure you know where it comes from. So what we're going to do is we're going to put those numbers down, this negative 2 and this 3. Okay? And then notice the multiplicities are 1. This helps you with quick sign analysis. Now, what we didn't do earlier, but we should do, is make sure we indicate that we have a 0 there. That's important when we do some rational inequalities. We plug in values like 4, positive, positive. Okay. Plug in values like 0. That'll be a negative times. Okay, I don't have to worry about plugging in values because I know the multiplicities are 1. I know we're going to pass through. Now we go back to what we were trying to find. We're trying to find negative values. When do we have negative values? Right here. And you'd say, x's belong to negative 2 to 3. Remembering that this means don't include. This means include. So make sure you have your brackets correct. If you ever see something where you have an inequality not equal to 0, it's not going to be easy unless you make it equal to 0 or greater than or equal to 0, stuff like that. So switch things up, move everything onto one side like this. Now you got 4 items. Pray and hope that if you factor by grouping, it works. We got 2 groups of 2 separated by addition. Okay. The first group, what can I factor out? An x squared from both of those. I have 2x minus 3. The second group, what can I factor out? Well, I want to get positive 2x minus 3. A negative 16 works out because negative 16 can go into 32 and 48. You get that positive 2x minus 3. Okay, obviously, you guys need to practice this on your own. Don't just look at me doing it. You need to figure this out and make sure you get the same thing here. Now, why do we do that? Because we can factor out that 2x minus 3 from both of the terms, leaving you what's left over, x squared minus 16 from this term. Now, all of a sudden, I realize x squared minus 16, that, my friends, is a difference of squares. The two numbers that add to get 0 x's and multiply to get negative 16 are 4 and negative 4. So this factors to be that guy. Now we can see our zeros. We got negative 4, we got positive 4, and then we have when 2x plus 3 equals 0. Subtract 3 divided by 2. Negative 3 halves. That's negative 1.5. So negative 4, negative 1.5, and 4. Multiplicities, 1, 1, 1. If we know the sign here, we know the signs are going to change around these zeros. These are zeros. I'm indicating that they're zeros. This is important. To the right of 4, positive, 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 change signs. Boom, 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 boom. I know that for a fact because of the multiplicities. When are we greater than or equal to 0? So positive values are greater than or equal to greater than 0. Zeros are equal to 0. So we need the interval here, including the 0, and the interval here. So my x's will belong to including -4 and including -3/2, and then or including 4 going to infinity. If you're not sure what that U means, it just means like or. It's like where my solutions are. You don't have to worry about the x belongs to either. You just get the correct interval. Notation is not uber important. All right. We're going to divide. Now, I don't like the division in this unit. I think it doesn't fit. But we're going to do it anyways. Not for my students, but for any student out there who wants to learn how to divide. Can't do this using synthetic division because it's not an x plus a number. This is a bigger thing, so I gotta do the long division. Now, just like we divide numbers, like 3 out of 8,152. What do? How many times does 3 go into 8? We do twice. We multiply, right? 3 times 2 is 6. Then we subtract. It's like, okay, this is 2. Okay, 3 doesn't go into 2 anymore. Bring down the 1. And then you put that 7 there, right? The same process goes here. How many times does this go into this? Well, it's like, how many times does x squared go into x to the 4th? Well, x squared times x squared gives me x to the 4th, right? So let's do that. But what do I do now? Well, what did you do here? 3 times 2 is 6. X squared plus 3x plus 2 times x squared. What does that equal? Okay, well, that's x to the 4th plus 3x cubed plus 2x squared. Now we subtract. Now, I don't like subtracting because people mess up, especially when we have negative numbers. I like to add the opposite. So I'm going to change this all into add the opposite. Now what happens? Well, we start subtracting, and then we can bring down some stuff. 6x cubed minus 3x cubed, 3x cubed. 11x squared minus 2x squared, 9x squared. Bring down the 6x just like we brought down the 1. Now, x squared plus 3x plus 2. How many times does that go? And that's the next thing. Like, how many times does 3 go into 21? And we said 7. And then 3 times 7. And then we put the 21 down here, subtract, and then put a 0, and then bring down the 5. And then we'll put a 1 here. That was the process. It's the same thing we do now. How many times does x squared plus 3x plus 2 go into this? Well, 3 times x gives me 3x cubed. Okay, so that will be a good start. I get 3x cubed plus 9x squared plus 6x, subtract those two, you get a big fat 0 remainder. Boom, we did it. This equals x squared plus 3x. Why is this helpful? It's like, well, if you knew that this divides into this can turn into a factored form. Is it easy to do now? This guy. Let's use synthetic division. If you have x plus a number, what we do is we like to put down the opposite of that number. This is so that we can add instead of subtract when we're doing things synthetically. And then we got the coefficients of my terms. Now we got 5x cubes, negative 6x squareds. I don't see any x's. Because I don't see any x's, I need a 0 there. And then I have the number 8. And then it's just a process. And this process comes from this. And it comes from the fact that we just have x and then the number. The process ends up being bring down the 5, multiply these two. And we bring down the 5 because it's 5 times a certain x to a power will give us 5x cubed because it's just x. Anyways, 4 times 5 is 20. We multiply diagonally, we put it there. We then add going down. That's why we use this opposite, so we can add. 20 plus negative 6 is 14. We multiply. Yikes. 14 times 4 is 1656. We add going down. Are you serious? This is ridiculous, this problem. 56 times 4 is 224. We add, we get 232. Okay, now I close this off. Why? This is my remainder. This is if this number was something other than 0. That would be the number. Now we go from right to left here. Remainder to the number to the x's to the x squareds. And if I kept going, it'd be to the x cubes, x to the fourths, etc. That tells me that this equals 5x squared plus 14x's plus 56 plus 232 x minus fourths. This is a whole, if there was a remainder here, we'd end like plus a third at the end, or plus whatever the remainder thirds at the end to make it whole. I don't trust that, so I'm going to check. I don't think I should be showing you this. X cubed minus 6x squared plus 8 over x minus 4. Yeah, look at that. 232 x minus fourths. All right, cool. So we got it right. All right. But let's move on to rational functions. We start with rational inequalities. And these are two of the hardest ones, okay? And just like polynomials, these are hard to do unless you got everything on one side and then 0 on the other side. So we should subtract the 3. Now you could do this a different way by multiplying by x minus 5. But if you do that, you need to keep in mind that the 5 is an important number because you're not allowed to have 5 in here. That would be a location of a vertical asymptote where signs could change. Anyways, after we do this, what do we do? Well, we want this to be like one fraction. And understanding that zeros or vertical asymptotes, if you have 0 over a number, you could change signs. Or a number over 0, you could change signs. You're going to find the zeros for the top and the bottom now, not just like for a polynomial, it's just the top. Now, to do that, we want one fraction. I write this as 3 over 1. I'm going to leave some space here because I subtracted 3. And to do that, we need a common denominator. So the denominator of this guy, I'm going to give to this guy. The only way you can do it is by doing the same thing to the top and the bottom. So you're multiplying by a version of 1. You're not changing what you have. You're just making it look different. And let's just be careful. I'm going to show a couple extra steps here. This is minus. This is 3x minus 15 when I distribute the 3. Now, you could have done this, or, sorry, this is x minus 5. Another way to make sure you don't mess up on the next step is to make sure you're distributing a negative 3. And that is shown because when you combine these two fractions, the 2x gets subtracted by the 3x to gives you negative x, but the negative 7 gets subtracted by a negative 15. A lot of people mess up on that. That's like adding a positive 15. Well, if you change this to plus a negative and distribute, you would have known this is a negative 3x, this is a plus 15. And that would have prevented the whole minus a negative thing. So I always like to change subtraction to add the opposite. It just prevents mistakes. So this is positive 8, the negative 7 plus the 15. And common denominators, you don't do anything, right? Like 3/4 minus 1/4. You don't do anything with the fourths. It's just 2/4. So this is negative 8 plus 8, x minus fifths. And this, my friends, is less than or equal to 0. Now, what is this telling me? Well, when you have a fraction where you could possibly change signs in a fraction, is that a vertical asymptote. If you plug in 5 into this, you get a 0 in the denominator. You're not allowed to divide by 0. It's not allowed. which is why at 5 you are undefined. Also, if you plugged in positive 8, I thought it was going to be negative 8, which is why I should be putting 5 over here. I should put 8 here, okay? This is undefined. This is a 0. Now we can do our sign analysis. Now, again, we could go off of multiplicities. The multiplicity of this 8 and this 5 are 1. So you know that signs are going to change around it. But be careful. If I plugged in 9, it'd be negative 9 plus 8. That's a negative over a positive. Negative over a positive, that's negative. Multiplicity 1, sign change, sign change. When are we less than or equal to 0? We are less than or equal to 0 when we have negatives, including a 0. Negatives don't include 5 because 5 is the location of an asymptote. It's undefined. So my interval is from negative infinity to 5, and it's also from 8, including 8 to infinity. This one's going to be messy, but whatever. Bleh. Yeah, let's just do it, whatever. 3x over x minus 1 minus, we're going to move everything to the left side, x over x plus 4 minus 3 is less than or equal to 0. What's going to be the common denominator? It will be x minus 1 times x plus 4. That's the only way we can get the denominators to be the same, which means I need to multiply this guy by x plus 4 over x plus 4. I need to multiply this guy by x minus 1 over x minus 1. And I need to multiply this negative 3 by both of them. So x plus 4, x minus 1, x plus 4, x minus 1. All right, probably going to have to distribute everything. So I get 3x squared plus 12x over x plus 4x minus 1. Keep that factored at the bottom. Minus x squared minus x over x plus 4x minus 1. Minus, I might as well actually distribute this. X plus 4 times x minus 1 is x squared plus 3x minus 4. This problem is a little bit messy. So if I distribute the 3 to that, it's minus 3x squared plus 9x minus 12. I think this is a little bit too hard for your test. Just FYI, guys. Okay. Let's make it easy on ourselves, right? Plus a negative plus a positive. Plus a negative, negative, positive. When we combine everything so that it's over 1x plus 4x minus 1, the 3x squareds and the 3x squareds are gone, leaving me with just one negative x squared. The 12x, I've already done the negative x squared. The 12x plus an x is 13 minus the 9. 13 minus 9 is 4. So plus 4x. Those are gone. Finally, plus 12. Fantastic. Now, make this something that's factorable. Pull out the negative 1 from all three of these terms. This becomes a positive, negative, negative. Two numbers that multiply to get negative 12 and add to get negative 4 are negative 6 and positive 2. This is nice. I mean, good job whoever designed this problem. So I got negative 1 x minus 6 x plus 2 over x plus 4 x minus 1 less than or equal to 0. Okay, fantastic. The top equal to 0, the bottom equal to 0 gives me 4 numbers. I got negative 4 from the bottom. That's undefined. I got negative 2 from the bottom, from the top, so that's a 0. There's no zeros over zeros, which are wholes. I got 1 from the bottom, that's undefined. I get 6 from the top, which is a 0. All the multiplicities are 1, which means the signs will change, but let's just figure out one sign, like 7. Everything's going to be positive except for this -1 if I plugged in 7. That's why I know that's a negative. Signs will change because of the multiplicities. Less than or equal to 0, negatives, including 0. So 3 intervals, -infinity, -4, -2 to 1, not including 1, including -2, 6 to infinity. Boom. Ukes. Now, oblique asymptotes are really just like what's going on as like a horizontal asymptote. It's like, what's the end behavior? It's a horizontal asymptote question. Now remember, for horizontal asymptote questions, when we talk about a rational function, we think about plugging in infinity. When we plug in infinity, the highest degree term is going to dominate as I plug in larger and larger values. Adding this, subtracting this, adding this will be like doing nothing, like adding a very, very small decimal to a very, very large number. As x approaches infinity, what's going to dominate the function is x to the 5th over x squared. Take those, divide, x cubed. That is essentially what this oblique asymptote's called. It's like, as we go off to infinity, you're going to be tracking what x cubed typically does. That's what an oblique asymptote is. Holes. Holes occur at 0 over 0. Let's like remind ourselves. X-intercept. 0 divided by anything is 0. A vertical asymptote is when you have a number over 0. A hole is when you have 0 over 0. Hold on. I gotta see. Alt-Shift-P should be pausing. I'm not sure if this is paused. Okay, back to things. Holes, 0 over 0. What you want to do to figure out if you have a 0 over 0, and to figure out when you have an x-intercept or a vertical asymptote, factor the top and bottom. If you get a 0 over 0, that's the location of a hole. Well, if I plugged in -5, that's 0 over 0. -5 would be a location of a hole for this one. But not 5. 5 is the location of an x-intercept, so that's gone. Let's look at this one. This is the same thing. X plus 5, x minus 5, x minus 5. Okay, plug in 5. 0 over 0. Hole. Boom. Let's see if there's another one. This one has a hole at 5, and it's got a vertical asymptote at -5. So hole at 5, that's what I was looking for. So that means actually the answer is D, B, and C. Come on, cursor. All right. All right, now we're into like the last day, which is graphing rational functions. And I did this in the video, it all comes down to the following. And it's easy. Set the numerator equal to 0. The numerator equal to 0, that's an x-intercept. That's when you get a 0 over a number. Set your denominator equal to 0. The denominator equal to 0, that's a vertical asymptote. That's when you got a number over 0. If you ever get 0 over 0, that's a hole. You can find the location of the hole by like canceling the zeros and seeing what's left over. You can look at a horizontal asymptote Horizontal asymptote is when you're plugging in infinity for x. You'll plug in infinity, and we'll do that in a little bit. Let's just start, and then we work on the sign analysis around our possible sign change locations, which are -2 and -1. So -2, -1, those are important. I have a x-intercept at -1. I have a vertical asymptote at -2. Signs, if I plugged in something like 0, positive over positive, these, sorry, that's a positive. The multiplicities are 1. I know the signs are going to change. So I get something like that. -1 is a 0. -2 is undefined. So, I mean, really around asymptotes, you got to figure out what's going on here. But before we do that and start worrying about those things, let's figure out the horizontal asymptote. If I plugged in very, very large numbers, the 3 won't matter, the 4 won't matter. I just get 3x over 2x. Simplify that. What do you get? 3/2. Y equals 1.5 would be a horizontal asymptote. So here, y equals 1.5, we have a horizontal asymptote. Okay. We could figure out how to trend around here, but it's kind of tough to figure out if you're like above or below a horizontal asymptote, unless it's around 0. So anyways, let's just kind of go for things. I'm at a positive side of things. I pass through -1, which is a 0. And then I'm going to be going down towards negative infinity towards my vertical asymptote. Like, let's look at a vertical asymptote. At -2, to the right of -2, I'm down here at negative values. To the left of -2, I'm up here at positive values. So like I can kind of see I'm going like this. Now, am I going to be underneath or above? Typically, if you like go from a horizontal asymptote, that's how you're going to be approaching things. It's not super important. And then to the left of -2, I'm above, and I'd be trending towards this horizontal asymptote here. That's what it's going to look like. Your domain is all x's, except you can't plug in -2, because that's your vertical asymptote. Your range are all y's, except you're going to approach but never get to 3/2. That's what the asymptotes kind of mean. No, if you pass through an asymptote, that's not the case. I don't think that's the situation here. X-intercept, vertical asymptote, boom. All right, let's fly through these. Ready? We got x minus 4, x minus 1 over x plus 2, x minus 2. We got 2 x-intercepts. That's the numerator. We got 2 asymptotes. That's the denominator. There are no holes because there's no zeros over zeros. Throw those numbers down on your friend the number line. -2, 2, 1, 2, 4. This is a 0, this is a 0, this is a vertical asymptote, this is a vertical asymptote. All the multiplicities of these are 1, which means you're going to pass through or change signs there. Not necessarily pass through, change signs. 4 is a 0, 1 is a 0. Here we go. To the right of 4, positive, 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 positive. Everything's positive. So I'm going to go positive, negative, positive, negative, positive. Let's find the horizontal asymptote. If I plugged in infinity, gone, 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 those will mean nothing. I just have x squared over x squared. That simplifies to just be 1. Okay, so y equals 1 is a horizontal asymptote. This is -2. This is 2. This is y equals 1. Let's start around my asymptotes. Like 2. To the right of 2, I got negative, so I'm down here. To the left of 2, I got positive, so I'm up here. Now, I'm going to pass through 4 and get to the positive land and then head towards my asymptote at 1. I'm going to go from positives to the 0 at 1, and then I switch to negative land. So I switch to negative land. I'm going to keep going negative down here towards -2. To the right, to the left of -2, on this side of -2, I have positive values. So I need to be above the x-axis up here. And I'll probably trend towards the horizontal asymptote, like above it from there. I pass through the horizontal asymptote at 1. So the domain is easy. It's all the x's except for -2 and 2. But the range is actually all the y's. I go from positive infinity down to negative infinity right here in between this vertical asymptotes, -2 and 2. Which is a little bit different, which is interesting. Okay. X cubed over x plus 1, x minus 1. X-intercept, x is 0. That makes the top 0. Asymptotes, -1 and 1 makes the bottom 0. No holes. Horizontal asymptote. This -1 won't mean anything. X cubed over x squared simplifies to just be x. Plug in infinity, you're going to get infinity. Now, that means you're going to be positive, positive infinity, negative, negative infinity. And it should be like approaching y equals x. That's your oblique asymptote, but who cares? I don't care. So, -1, vertical asymptote. 1, vertical asymptote. 0, 0. Sine analysis. -1, 0, 1. This has a multiplicity of 3, so it's going to bend. So, and then the other has a multiplicity of 1. That's important. Checking signs, we have positives, negatives, bending through positives, negatives. So here we go. Positive until 1. Then we go to negatives. How does that work out? Oh, to the right of 1, we're positives. We're up here, going up here. That's like, make sure you find your correct arrow around your asymptote. Well, I'm to the right of 1, I'm positive. And then I have to trend towards like y equals x positive. To the left of 1, I'm negative. I will bend through 0 because the multiplicity is 3, and I'll come up towards the positive infinity around -1. To the left of -1, I'm negative, but then I'll trend towards that y equals x oblique asymptote. I want to graph this. X cubed over let's use decimals. X cubed over x squared minus 1. Boom! Look at that. Domain. All the x's I could plug in except for those vertical asymptotes at -1 and 1. Range, I can have all the y's. I pass through all the y's. All right, cool. A couple more to do. All right, x-intercepts, -2, top equal to 0. Asymptote, 1. The multiplicity of that 1 is 2. Holes, none. Horizontal asymptote. This is a tricky one because it's like x plus 2. In the denominator, that simplifies to be x squared, ... The other stuff doesn't matter. You just get x over x squared. Well, that simplifies to be 1 over x. If you plug in infinity in for x here, what happens? 1 over some super, super large number? That's 0. So that's important. Y equals 0, horizontal asymptote. X equals 1, vertical asymptote. X-intercept at -2. Let's do the sign analysis and see what this looks like. -2, that's a 0. 1, that's an undefined. I do not change signs around 1. So if I got to the right of 1, positive over positive, I do not change signs because of its multiplicity. I do change signs here. Okay, so what does this look like? Well, I'm trending. Okay, I can kind of see what it's doing. Let's look at the asymptote. I'm up here towards the positive side of the asymptote if you're looking at either positive or negative, because I got positive to the left and positive to the right. So I got positive here, positive here. I'm trending towards the y equals 0 asymptote. But here I have to pass through this -2 to be in the negative side of things and trend towards the asymptote on the negative side of things. We'd be able to see that x plus 2, x minus 1 squared. See, it's like tough to see, but positive, but staying positive. Positive going through the 0 at -2, and then being on the negative side of things, but going towards the horizontal asymptote of y equals 0. Pretty cool. The domain, all x's except for my asymptote at 1. My range is tough to describe because I don't know what the minimum value is. You can find the minimum value using calculus, but you don't know what the minimum value is. Next year, if you take AP Calculus, you will learn how to take the derivative of this, set it equal to 0. Don't worry about it. I wonder what they say in the key for this. So it's like y's, bigger than or equal to 0, but there's also some extra somewhere, some y's that are going underneath. Like I guess if you zoomed in, it's like, oh, I get to negative 0.083. Maybe this is like at -5. And like, that's it. And it's like, how do you get -5? Where does -5 come from? Calculus can show you that. So it's actually y is bigger than or equal to negative 0.83. And you guys don't know that. So, okay. It's not important. Finding the horizontal asymptote, that's important. All right, here we go. We're going to have a hole. We got x plus 3, x minus 3 over x plus 3. The top equal to 0. I'm just going to put down 3. The vertical asymptote, I'm not going to have any because if I plug in -3, I get 0 over 0. I finally have a hole. Now let's find the location of the hole. What happens if I plug in -3? Let's see. If I plug in -3, I would get 0 times -6 over 0. Well, let's just pretend you can cross out these zeros. You get -6. -3, -6 is the location of the hole. That's like canceling this out and then plugging in -3, you get -6. So X-intercept at 3, at -3, -6, I have a hole. My graph looks just like x minus 3. It looks just like that. It's going to end up being a straight line, a linear equation, what it's going to look like. I guarantee you. If you wanted to kind of check the horizontal asymptote, you can kind of see, well, x squared over x simplifies to be x. This is like the oblique asymptote. You're going towards like a y equals x kind of deal. You can find the y-intercept too in this case. You got to find the y-intercept in the other ones. The domain is the x's, except I can't plug in -3 because I get 0 over 0. The range are all the y's, but I don't actually get the y value of -6 because of the hole there. Good question. There's one asymptote at x equals 5. There's no holes. There's no x-intercepts. The horizontal asymptote is 0, y equals 0, x equals 5. To the right of 5, I'm going to have positives. To the left of 5, it's negatives. Positives trending there, negatives trending there. My domain are all x's except for 5. My range is all y's, except I don't pass through 0 in this case. That was a silly one. This one's tricky. What we probably should do is make it one fraction. X plus 3 over x plus 3, right? Just like we did with inequalities. 1 over x plus 3 plus 5x plus 15 over x plus 3. This is 5x plus 16 over x plus 3. Yep. X-intercept is going to be x equals negative 16 fifths. Great. Asymptotes, x equals negative 3. Holes, none. Negative 16 fifths is close to negative 3. Asymptote is at negative 3. Well, that's going to be weird. Negative 16 fifths is bigger than negative 3, so this is on the right side of things. I'm going to just be exaggerated. Okay, so asymptote, 0. Okay, this is tricky, the next part. The horizontal asymptote. Okay, it's like, oh, cross off this 5, cross off this negative 3. Actually, no. Stop. Use this. Use this. This is nice. If you plug in infinity, the 16 goes away, the 3 goes away, you just ignore it. 5x over x, 5. That's beautiful. Look at that. I might use this in calculus in the future. I usually just told the students, well, if you plug in infinity, this goes to 0 plus 5. It's another way to figure out that the horizontal asymptote is 5. So here we go. Let's do a sine analysis really quickly. Negative 16 fifths and negative 3. The multiplicities are 1. It's going to be positive, negative, positive. Okay, so positive trending towards y equals 5. Negative through there, positive. Okay, that's not that bad. Let's see that. 1 over x plus 3 plus 5. Oh yeah, there's negative 3. There's the negative 16 fifths. Boom. Domain, all x's except for negative 3 range, all y's except for, we never really touch 5. We don't go through 5. We just approach 5. What is not a vertical asymptote? 0 is not a vertical asymptote. Actually, no, 0 is. 0 is a whole. Yeah. X squared plus x minus 12. X is not a vertical asymptote. It's a whole. Sweet, we did it. See you out there.